So, welcome to the second lecture, Advanced Thermodynamics and Fluid Mechanics on oblique shocks. So, first thing we do is we just recap what we did in the previous lecture. So, lecture 1 was on normal shocks. And we analysed the flow properties through a shock in the shock frame reference. So, that was akin to the shock, akin to almost standing on a bridge and seeing the fluid or the flow go past. So the lines here are drawn streamlines, they go past our shock structure. On the left hand side and the right hand side, the flow is pretty uniform, and so the only gradients that are important are those of the cross. We used 3 conservation laws, so we use mass, momentum and energy. And mass can be described in terms of words of what goes in goes out, or mathematically rho 1 u1 equals rho 2 u2. Momentum conservation can be described in terms of the increase in momentum flux is equal to the decrease in pressure. So there we go, rho 2 1 rho 2 u2 squared minus rho 1 u1 squared is balanced by the decrease in pressure. And conservation energy, you can go through a number of ways. You can say the internal energy plus the pressure work potential plus KE is conserved. Or the other way to do it, which we went through in detail, is that T plus a half gamma minus 1 m squared is equal to the stagnation temperature, that being conserved or constant across here. And we need to couple that with the equation of state, P equals rho RT. R here being the gas constant for the configuration you've got, so R is actually ideal gas coefficient over the atomic mass in kilograms. The main features of this flow were that the flow would go from super to subsonic. And if you remember, we had this discriminator of the Mach number being the local speed of sound, so local velocity divided local speed of sound varies spatially, and the speed of sound in this case is square root of gamma RT. The main features of this flow were that M1 is bigger than 1, M2 is less than 1, and we dismissed the other solution, which was flow that's possibly go from subsonic to supersonic on the grounds that the entropy would decrease, which is not second law of thermodynamics means that that's not possible. The other solution we met was M1 equals M2. This is a normal shock, which means that the streamlines are normal to the shock feature. So this angle here, it's got 2 elements. One is that the shock angle is 90 degrees, and the other thing is that the deflection of the streamline is 0. Those are 2 quite critical elements. We are going to have a flow where delta is 0 and zeta is not equal to 90 degrees. We're going to have that for a case of an oblique shock, and that's a very special case where M1 equals M2. And so this is not a solution to be dismissed. So these are both important. So in this talk, we're going to be looking at the configuration where the flow is deflected. So the streamline's coming in and turn, and they turn as a consequence of the presence of a shock. And that's the main feature of this problem. Now, it's analytically quite challenging. Some of the concepts we take from normal shocks we can apply to oblique shocks, but conceptually, so mathematically, it's a bit more challenging. So we kind of make use of graphical solutions and a compressible flow calculator in this particular case. So let's see how this story unfolds. Fluid mechanics is such a diverse area that many of the concepts we develop for this particular course on compressible fluid mechanics can be applied to other aspects of engineering and fluid mechanics. So, and one very obvious case is the case of flow in shallow water. So both compressible flows and shallow water flows both can support waves, and a lot of the mathematical machinery that is used in both. There are very important physical differences, and the first thing is that we use in shallow water flows is we use what's called a Froude number, which is equivalent to our Mach number, and it's defined in terms of the depth averaged velocity divided by the speed of fluid, wave speed on shallow water, which will be square root of g times h, being the water depth. So this is a very important type of analysis that's used in river flows, tsunamis, storm inundation for shallow waters. And we use the language quite similar to compressible river currents. We use the language of Froude number being less than 1 as being subcritical, Froude number bigger than 1 being supercritical. The Froude number is actually a concept really taken from the marine engineering community, who first looked at the resistance on ships due to their speed and shape. And one important part of their drag is actually the wave drag. The waves generated as the hull goes through the water is a pretty critical component to that drag bit, which is why Froude studied it and characterized this in terms of a Froude number. So you can apply conservation of energy, conservation of, well, energy doesn't work so well, of conservation of momentum, conservation of mass in this particular case. The change in specific energy is actually used to look at dissipation. Dissipation is important in weirs and stuff because that's how you reduce the momentum of your stream. It's too fast, it'll start eroding the ground. And as I've explained to you before, I use all of the tools that we've described in this course to look at flow past buildings due to tsunami or channel flows. And so this is the case downstairs in the laboratory where I looked at, or one of the first kind of types of experiments where I looked at the state of the flow due to flow past this obstruction. And what's interesting, and so we've done a lot more work on this, is if we look at the Froude number upstream and the Froude number downstream, what happens is that the flow jumps into a lock state, and then there's another branch over here. So we've done this experimentally, computationally, and this is important. So if you have a tsunami past a group of buildings, what happens is as the flow speed increases, it jumps to this critical flow state, which is quite important, and it's characterized, as we see down here, by a very large difference in water height between one side and another of the building, and elicits a very large resistance force, which causes it to be swept away. And this is essentially a jump. So if we look at this example in a kitchen, this is me pouring water from a tap onto the basin in a kitchen, and as you see, it creates this very fast radial jet on the surface, and this is a supercritical flow. And what happens is that there's a transition determined by actually the water depth far away, akin to the pressure far away from your also the fact that the flow is diverging, so the velocity does decrease with distance. And there's a fundamental jump from the subcritical to a supercritical state, and this is the hydraulic jump. And a hydraulic jump is essentially equivalent to a shock. Now, as we've mentioned a few times, the Mach number is defined in local speed divided by local speed of sound, and so this is a variable that varies spatially, unlike characteristic variable that varies spatially, unlike something like the Reynolds number, which is a kind of characteristic of the state of the flow. And so what we're going to do is we're going to introduce a kind of a terminology that allows us to discriminate between one process and another. Now, the first thing to note, as we've met before, is that the a shock represents an increase in pressure, a decrease in stagnation pressure. The stagnation temperatures we've discussed before, T0, and we looked at that as a concept, is a conserved quantity for adiabatic flows, and so it's going to be constant across our shock. And the other features we've discussed before is that a shock is a region where the flow properties change very quickly, and that's going to be useful in our analysis. When we look at the flow over here, we've got a streamline past a bullet. In the frame of reference of the bullet, the flow is in the direction, it's deflected around the bullet, and it comes back to its original position far away. And what we see here is that this shock is at an angle to the incident streamline. That angle is important. That means that it's an oblique shock. So oblique shock still causes the flow to be squashed, but the flow is also deflected. And there are two types of oblique shocks. We call them weak oblique shocks, strong oblique shocks. There are kind of subtleties related to this, but the simplest way to describe them is a weak oblique shock, which is really what we mainly deal with, is the case where the flow is supersonic both sides. So remember, a normal shock went from supersonic to subsonic. That's a very rapid change in pressure and reduction in stagnation pressure. For a weak oblique shock, the Mach number difference is generally much smaller. A strong oblique shock is like a normal shock in the sense that the adjustment across it is very, very strong, very dramatic. In this case, the flow is supersonic on one side and subsonic on the other. Now, in order to start our discussion of oblique shocks, we just need to start off our discussion of what is a streamline, because we're going to find those are important. Now, streamlines tell you at an instantaneous time the direction of movement of the fluid particles. And so if we had a series of little tags in the flow, their instantaneous direction, if we took a sign of like a shot just a millisecond later, their direction will tell us where it's moving. And we can actually integrate this position over time, so over a fake time, in order to connect these streamlines together. Now, for steady flows, streamlines are very useful, and they're quite good as being able to use, well, you can apply them as a way to look at mass conservation. Unsteady flows, other types of discriminating tools are quite important and a bit more useful. Now, they tell us information about the local velocity field, but they don't tell us about the local speed. They're basically an indication of direction. So streamlines have direction, and as a consequence, we always draw arrows on them. There are other things that you've met in year 1, path lines and street lines. Path lines being the passage of a fluid element, and street lines being sourced from a single point. The streamlines are quite important. Now, the critical thing about streamlines is that they have a very specific characteristic. For incompressible flows, they never cross. So if you were to draw a streamline pattern and you draw things like that, then this wouldn't be true. Yeah, that would be wrong. And so they don't cut into one another. This concept that works in 2D and 3D, a bit more difficult to interpret in 3D. And they can't go into rigid walls unless they're being pulled in. So there are two special cases of streamlines meeting rigid bodies. One is it meets at a stagnation point. This is a very special point in the flow itself and has a particular topological meaning as a node. This is a half node because you're not seeing the other part of it. You can add up the number of nodes and half nodes in a flow and the number of saddle points and the number of centres, and the sum and difference of those are equal to the genus of the topology of the surface on which we're drawing them. So it's a very useful concept. We've used it before to look at flow structures in the choroid capillaris in the eye, and it's from Euler's theorem from about 1750. So it's a really topological reflexive fluid mechanics, very important. So streamlines only meet rigid bodies at these stagnation points or where the mass is being removed or added. And the surface of a body is a streamline because flow doesn't go through it if it's incompressible and nothing's. So that's quite important in our next discussion. Continuing in our terminology, defining our terminology for oblique shocks, there's actually just two types. We're going to see this featured quite a few times. There's ones that are determined by purely geometry. The fact is the flow must be deflected around something because the streamlines can't go through it. And that's a geometrically controlled shock, oblique shock. The other one is what we call a pressure constrained shock, pressure controlled shock. And so if we're looking at the exit of a rocket, there's usually a pressure mismatch between the exit velocity, exit pressure and the back pressure. And the only way that you can adjust that is through the production of oblique shocks. And so, so we have these two types of oblique shocks, geometry controlled, pressure controlled. So to analyse these flow processes, what we're going to do is look at a prototype problem of a geometrically constrained flow, controlled oblique shock, and we're going to look at the deflection of a streamline in the vicinity of this wedge. So we've got our wedge. We're going to assume that the wedge angle is delta, and we're going to, well, we don't need to assume it's small, but it's a delta. The flow is coming in. Now the streamlines must necessarily be deflected by the presence of the body. They can't be parallel. They can't go into it. They can't go away from it. They must be parallel to the surface. And that deflection at high supersonic flows gives rise to a shock. That's the way the flow will adjust. We're going to use the notation of zeta, the Greek symbol, to denote the what we call shock angle, which is the angle between the incident streamline and the shock. This is 2D, so we're not looking at curvature effects, and we're going to use the notation 1 before and 2 afterwards. Now, how we analyse this, as we analyse most of these problems, is we look at conservation principles applied across the shock itself. And to do that, we'd have to look at conservation of mass, momentum, and energy. And momentum has two directions, so we're going to have two equations for that. So what we need to do is we need to resolve the inlet upstream velocity and downstream velocity components which are parallel to and perpendicular to the shock itself. So here we're going to use the notation n for normal and t for tangential, and of course we get this by resolving those components. So if we look here, u1t is just going to be u1 cos zeta, u1n is u1 sine zeta. We can do the same with the downstream components, but here we just need to take into account the fact that the angle here is now zeta minus delta. Now the conservation principles that we apply, as we said before, there are three of them. But the momentum is a vector equation, so there's going to be two equations here. There's things I've drawn are coloured in blue. You will have met when you were doing some vector analysis in year 1, perhaps year 2, which I did from grad. This is kind of vector shorthand. As we've said before, really it summarises for mass conservation what goes in goes out. Pressure, increase in momentum flux is counteracted by decrease in pressure, and energy, sum of internal energy plus pressure work potential plus Ke, or specific Ke is conserved. So we're going to apply these, we're going to integrate these across the shock and determine the relationship between before and after the shock. It's worth just recapping the normal shock relations and how they were derived. And so if you remember before that the conservation principles for mass were based on the flux through the shock, and so that ended up being the normal velocity. The increase in momentum flux equals decrease in pressure. The momentum flux is the momentum flux normal to the shock, so it being u in subsequent n's, but the energy was a specific ke. So in that particular case, we've got velocity squared, and velocity's got a u 2n squared and a u 2t squared. And for the normal shock, remember, there was no tangential velocity, so they kind of dropped out. And we'll see that that's quite different from an oblique shock. So that would have been u1t, u1t squared. But this would have been 0 for a normal shock. For an oblique shock, things don't change very much. This is still the same. This is the same. But we've got this addition, and this is the same. What are tangential components of velocity upstream and downstream. The most critical bit is this conservation of momentum parallel to the shock, the oblique shock itself, and that comes from the fact that there is no pressure variation along the shock itself, and no instantaneous acceleration, and this altogether means that the tangential component is conserved or constant across the oblique shock, basically ut2 equals u1t. Now that's important because if we take that constraint and put it in the energy equation, we find out these two terms cancel out. And so that's a great simplification and begins to look quite a bit like a normal shock relation, except now we will start to have to deal with not the full shock, but something that looks like that. Define our Mach numbers in normal shocks. We can use normal velocities. We can use the normal shock relations. So if we do that, what we need to go back is look to see how we define our normal velocity. So our normal velocity in this particular case, we've got a normal and our tangential components. The tangential component tells me that these two are going to be equal, which gives me one relationship, and the fact that the equations look identical to the normal shock relation, except expressed in terms of Mach numbers that are themselves expressed in terms of normal velocities, means that we can go from the normal shock relation to a relationship between what happens on the left hand side and right hand side. Now, in contrast to a normal shock where we go from m1 and we get m2, here it's slightly more difficult. We're talking about a relationship between deflection angle, shock angle, Mach number 1 and Mach number 2. So in some cases we need at least two pieces of information to get the other ones, O and pressure. We need at least two bits of information. Now, how we do this, as you could probably see, it's not solvable with a simple analytical expression, but a relationship, a nonlinear relationship between the key variables. And so, in order to make use of this formula, we basically make use of shock charts or a compressible flow calculator. So ultimately, we don't have a solution that m2 is a function of m1. We have a relationship between all of these variables, and if we know two of them, we can work through that process and discover what the rest are. So one of those relationships is a relationship between upstream Mach number, shock angle zeta, deflection angle, wedge angle delta. And so here we see this plotted one against the other. So the normal shock that we met already is when zeta equals 90 degrees. And in this particular case, the Mach number can vary from 1 to 3. In this particular case, actually, delta is 0. We have another branch here, yeah, which is delta is also 0 and zeta is less than 90 degrees. And this is a solution where M1 equals M2. So if we were given a Mach number and a deflection angle, a wedge angle, then we would take our Mach number, let's say Mach number 3, we'd look at 20 degrees and we'd find out where that occurs. What would the consequence of that be? And so here we're talking about something like 38 degrees, the shock angle of 38 degrees. There are other tables, and you've been given those, or there are electronic versions of those on the Moodle webpage, and the ones we've used in the past for teaching students how to solve this problem. Now this figure will highlight some of the really important and quite interesting parts to supersonic flow past wedges, which is the idea that there are multiple solutions states. And so we'll just give an example of something that starts off with a Mach number of 3. So here is something where it shows a relationship between delta, deflection angle, wedge angle, zeta, shock angle, Mach number upstream. And these isocontours are basically isocontours of Mach number, M1. So M1 being 3, this is the example we're going to look at, is actually this curve here. Going to look at the case where the flow is deflected by 25 degrees, small deflection, which is not small, but medium deflection and a large deflection, and let's have a see what the outcome of that is going to be. So if we have a deflection of 25 degrees, so we look on the left hand side 25 degrees and draw a line across, what we see that there are going to be two solutions. There's going to be a case that sits on the left hand side, which is where the Mach number is supersonic, downstream is supersonic, and that's going to give rise to a weak shock with a deflection angle of about 45 degrees. This is this one. And there's going to be a strong shock here. It's about 78 degrees. So two possible solutions. If we make the wedge angle thicker, what happens is that the strength of the shock goes up. You see here is that drawing of 34 degrees, draw that line across, this only intersects this curve at the top. In this particular case, it's in the strong shock case, and there's only one solution. As we increase that increase that deflection angle, make the wedge much thicker, then what we find is that there is no solution. This curve for a wedge angle of 38 degrees does not intersect this solution, and so in this case there is no solution. So what happens if there's no solution? So what happens if there's no solution? It doesn't mean that it physically can't happen. It means the adjustment occurs in a different process, and that process obviously our assumption is based on the shock being generated at the leading point of the wedge. And of course, how it physically adjusts is it creates a bow shock at the front and sits proud of the obstacle itself. The process of adjustment then has some more complexity. So here we see the same thing, and just shows you the outcome of the solution. But if the deflection angle is small or smaller than the critical value, then we end up with possibly two solutions. Mach number coming in, just Mach number 2. In the far field, that's the near field configuration. In the far field configuration, the shock will tend to weaken with distance, and so what that happens is it tends to be a shock wave, and the angle to the incident streamline end has an angle of 10 to the minus 1 over Mach number. We'll meet that when we look at expansion fans in lecture 3. And the flow ultimately far away becomes sonic. Actually, the far away becomes linear, and the wave moves with speed c. Now, when the wedge angle is very large, and this is exploited on satellite re-entry craft, space re-entry craft, you generate a bow shock which sits in front. So at the front you're going to have something that kind of looks like a normal shock in this vicinity, and the flow is going to be subsonic after that. The flow is being squashed and then expanded, and so what you're going to see is you're going to see the formation of a critical layer, a critical region, and the flow becomes supersonic after that. So the flow is being squashed and expanded, and ultimately supersonic after that, with at the sonic line. Yeah, that's the point where the Mach number is 1. So this shows the relationship between Mach number 1 and Mach number 2 and the deflection angle. As we've said before, there are two kind of states for deflection angle be 0. You see the line above here, the red line here, is that solution M1 equals M2. That corresponds to a weak shock solution with no deflection, and is really characterized by an angle, a non-zero shock angle of zeta, which has a value of arc sine 1 over m. This is an isentropic process. The Mach number is unchanged, but and it's quite important when we kind of look at expansion transformation. The other solution, which is the one where the flow downstream is subsonic, is the normal shock relation. We've met that in lecture 1. So in this particular figure we show the variation of pressure ratio across the oblique shock versus the shock angle. Since we're dealing with oblique shocks, then there must be a pressure rise across that shock. So P, the only physical situation is that P 2 over P1 is bigger than 1. This red region, although we can contour it up, actually corresponds to the case of nu, or actually corresponds to the case of delta being less than 0, deflection angle being less than 0, and so that's unphysical, and so all cases correspond to P over P1 bigger than 1. Now where this graph becomes important is when we're dealing with pressure constraint problems, and for instance an example of that is the exit flow of a rocket engine. So if we draw combustion chamber, throat, nozzle associated with the rocket, we will have an exit pressure PE. So we'll be discharging into the local environment, which has a back pressure PB. These external flows, the back pressure is essentially the atmospheric pressure, and that has an important consequence on the efficiency of the engine. So at sea level, what we tend to see is the atmospheric pressure is very large. In this particular case, P back pressure is usually bigger than the exit pressure, and the only way the flow can adjust, the only way for the pressure can increase up to that value is through an oblique shock. And in this particular case, the pressure is lower than we need, and this is what we call an overexpanded. The flow has been expanded too much. And there are situations when the back pressure is less than PE, and in this particular case the exit pressure needs to be reduced, and so this is really a case of what we call underexpanded. You haven't expanded enough. So just to summarize the types of things we have two types of shocks. We have a geometry controlled or constrained one, and a pressure constrained. Usually with geometry constrained, what we're given the deflection angle of the streamlines and the Mach number, and then we use to determine the downstream Mach number, the shock angle, and the pressure ratio. For a pressure constrained problem, we're actually given usually P2 over P1, and we're given M1, and then we have to go and find the deflection angle, shock angle, and M2. These occur in two quite different problems. Pressure constrained one, we're doing it nozzles, outlet flows, and these types of things. Geometry constrained, we're doing usually about the inlets of a jet engine or the flow round lifting services. We've got a discriminator between the types of shocks we have. We have oblique shocks, we have weak shocks and strong shocks. Very crude, but the general way of describing it, a weak shocks are when M1, M2 are both bigger than 1, both supersonic. A strong shock is the case when M1 is bigger than 1 and M2 is less than 1. That's a very crude way of describing it, but more or less a reasonable approximation. So this one more or less concludes our discussion of oblique shocks. We've taken some analysis of normal shocks, we've adapted that, we've discussed the conservation principles. The momentum equation has a vector form, and that means that the slip across the shock itself is 0. And we've discussed the types of solutions occur. We can have two solutions, one solution or no solution. The consequence of having no solution doesn't mean that there's no physical adjustment. It means that adjustment isn't characterized by a pin shock at the front. We have to bear in mind this is a 2D analysis. Approximations can be made for 3D axisymmetric flows, slightly more complicated. G.I. Taylor published a couple of papers on this. And so what I would do now is start to go through the tutorial sheets.